let's start from certificate quality. So in the last 2 weeks, we continued and completed the final code review sessions about the certificate quality implementation. So a few more changes were requested, and the changes were implemented, reviewed again, and approved. So the certificate quality is currently developed and finished. Always regarding Zendu, we proceeded with the seized sidechain withdrawal mechanism. And this is something that, is related to the main chain part of the seized sidechain withdrawal and not specifically to the circuit implementation. So, we proceeded with this in parallel with the certificate quality. And just to have a short recap, this is the mechanism that allows a user to withdraw the funds from a sidechain that is considered. So, if for any reason a sidechain is going to cease, our model have a mechanism that allows the users to withdraw the funds from that sidechain. And consider that, this doesn't imply the interaction with the sidechain. So the, magical thing about this mechanism is that the user will be able to prove to have some coins in the sidechain without having to interact with the sidechain itself. And so, and these will allow him to withdraw them and have them available again on the main chain, even if the sidechain was seized. So, so in the last 2 weeks, we were able to complete the design of the changes that are needed on Zendu, and this has been analyzed in details, and we already started with the related development activities. And in particular, so far we already did most of the core structural changes, and all the changes that are needed. For example, we have to introduce some specific output in a transaction that allows you to provide the proof and the claimed coins and so on, and this part has been already finished, and we are now working on the verification logic of the proof and the collection of the public inputs that are needed to be provided to the proof verification. Okay, and this was related to the seized sidechain withdrawals. Always related to the Zendu activities, we started working on the main chain backward transfer request. And this is another type of the so-called main chain managed withdrawals, as it is the seized sidechain withdrawal. And it's used to, let's suppose that, very quickly. Let's suppose that you have a sidechain that is totally maliciously controlled, and that is even, censoring withdrawal requests on the sidechain side. So because it's completely maliciously controlled. Okay, we wanted to provide a way for the user to be able to withdraw his coins, even in such extreme situations. So we have a sort of a request that can be performed on main chain that force the sidechain to process it and to answer to it. And so if the circuit on the sidechain side when process this request, if this request is legitimate, requires to add the relative withdrawals in the next certificate. If the circuit is written in that way, a user will be able to withdraw his funds even with a completely maliciously controlled sidechain. And so we have been working on the design of the changes that were needed to introduce the functionality on the ZenD, and we already started the development activities. And so, you will hear more about these also during the next weeks. Okay, now switch topic and let's go on with the proving system. As you probably will remember, before Christmas, we announced that our research demonstrated a huge performance improvement on the recursive proof composition timings. And I mean, we have been working on a proving system with an accumulation and deferred validation scheme that allowed to significantly cut some of the most expensive operations that are needed by the intermediate proofs. I mean, we were able to cut on the intermediate. We are able to cut on the intermediate proofs some very expensive operations, and defer them just at the end. I mean, for example, at the end of the epoch. And so this is let me say a modification on the proven system that we have been designing, and currently we're working on. We had several sessions with the developers of the proving system. I mean, the team of that is working on the proving system, and we have been sharing the ideas behind this improved design, and we're identifying all the changes that are needed on the proving system implementation. For example, as I was saying before, we're going to change the intermediate proof structure to carry on the needed accumulators, and obviously we are going to change the proof verifier and the prover to manage these additional elements accordingly. So this is just an example of the many changes we are looking in detail in this session between the proving system team members. And the implementation of these changes will follow. I think that this is something that is going to happen very soon. Maybe even from the next week, we will be able to start implementing the changes accordingly to the new design of the proving system. And obviously, as you will remember, we also proceeded with the GPU improvements, and in particular, in the last 2 weeks, we were able to get the gingerlib integrated with our GPU improvement code, and getting Marlin rebuild using gingerlib instead of the ZXL library. So because we started, let me say, doing these GPU optimizations on some library, but then we wanted to port all the changes integrated in gingerlib, so to have everything, I mean, in a unique library. And all these has been completed and tested, and all the benches were reran to check that everything was working properly, and so no slowdown on the algorithms after switching to this implementation integrated with gingerlib. Next step is porting also the CPU improvement as well in gingerlib. Okay, and that's it regarding the proving system. Okay, and coming next is circuits. Okay, regarding the circuits, we already start developing the Rust circuit SDK, and in particular, we have been working on a way to create based transaction circuits that are customizable in a way that you can easily add new rules, new transactions, and in addition to the ones that are provided by our model. In parallel, we kept working on the design of the multiple circuit that we have developed. And in design, writing a specification, a very detailed specification of all the witnesses, all the public inputs, and all the statements that needs to be proven for each of the circuit that we have to develop. So, and this was an enormous work that we had to do, but it's very useful for the development phase, because the developer now has a very clear idea of what are the witnesses, what are the public inputs, and what has to be proven, and so what are the things that needs to be checked. And so this was another very important step in the circuit implementation. By the way, we have already started also working on some part of the circuits, and this is something that we are going to work on for the next weeks. Okay, and this is related to the circuit, and let's switch to another topic that is the BitVector, and especially on the SDK side. In reality, as you probably remember, we are using our model have a way for dealing with data availability attacks. So this is something that are let me say, a very dangerous thing that, if not managed properly by the design, can be an issue. So our model take in consideration these, and so we're able to provide a way for the user to withdraw their funds, even if the decision was totally maliciously controlled, and even if the data behind the states committed in the main chain are completely unknown. So someone took the control of the sidechain, hide the blocks, hide everything, committed the state, and everything. Was conformant to the circuit, but no one knows the data, no one can continue the history. So how the user will be able to prove that he still has some coins in the sidechain? So we have designed a solution that allows to do that, and allows you to prove that you had some coins in the past and that coins are still there. And this is done by, publishing a BitVector that keeps track of the position of the UTXOs that has been kept untouched for some epochs. So, but okay, beyond these details, we have to keep track of this BitVector, and so we are working on a Merkle tree, UTXO Merkle tree implementation on the sidechain side that automatically keep tracks of this BitVector every time you move at UTXO and so on. We'll keep track of it, and so at the end of the epoch, will be very easy from the SDK perspective to retrieve the BitVector in the compressed form, and publish it within the certificate, and have all the data already calculated. So this is something that the BitVector is already implemented, but we are currently integrating a unique extraction that it will be called the Zenbox Merkle tree, and this will be exposed, and this functionality will be exposed to the SDK. Okay, the very last topic, sorry to be so long today, is the sidechain explorer. It was mentioned in the last Weekly Insider, and we have been working on the SDK in order to allow the future support of a sidechain explorer. So we finished to implement the WebSocket server architecture on the sidechain node, and we added the needed endpoints by the sidechain explorer. So currently, also the unit test, integration tests were added to. So now we are ready for a first code review iteration of this sidechain explorer. And yeah, probably this is all for today from our side. Back to you, Luca.